position, and we take the time derivative of the position, then we can get velocity. Then again, we can get acceleration. And we know that for Newton's first law, so it's F equal to ma. So if we want to know the force, we need to know the acceleration. So that is what we learned in the basic physics, right? But now, so if we want to do the Jacobian, the force domain, so normally we need to find the acceleration. So for the easy way is we found the acceleration or angular acceleration, then we can find the acceleration of the n factor. Then we can do the force. But there is another way. So today we're teaching you is using the principle of the virtual work. So how can we calculate? By using the virtual work. So we know a work done is equal to a force times a displacement. So this is the work done. Is this okay? Still remember the work done? So it's force times displacement is equal to the work done. And if we see in our joint, so if we have like a very, very small displacement, angular displacement within the joint. So if we apply the torque, like we apply a torque on the joint, so the joint will be rotate, right? So like, if there's a joint, so if we apply a torque on the joint, so if we apply a torque, so even if this is a rigid body, there should be a very, very, very tiny amount of displacement, like a virtual displacement. So because it is a rigid body, so it shouldn't be rotating, but we assume that because this is a joint, so if we apply a torque on this joint, so there will be a angular displacement rotating. So what is the work done of the, if we apply a torque? So we apply a torque and the displacement of the joint rotates theta. So this is the displacement of the joint. So this will be equal to the work done. So is it okay? If we see in one joint, so will be like this. And another thing is that if we see at the n factor, so the n factor, if we apply a force, so if we apply a force on the n factor, it should have a very, very tiny, small displacement. So it's like, if this is a joint, so if we apply, I'll use the color. If we apply a torque on the joint, so it will produce a very tiny displacement, angular displacement. So if we times the torque with the angular displacement, we can get the work done by the torque. So we can call this the work done by the torque. And at the n factor, so maybe here is the n factor. So if we apply a force at the n factor, and then the n factor will be slightly move a very, very tiny part, the tiny displacement, we call it the delta x. So the work done by this force is equal to we can call it the W. Or this is because we use the external force, or we can call it WE, external force. So this is the external force. So this is the external force, and it's applied on the A factor, and it's produced. The work done of this force is F times delta X. So if we see it together, so if there's a manipulator, external force is applied on the A factor, and all the joints need to resist this deformation. So they use the torque, and this is the deformation. So these two will be equal. Is it okay? Because when you apply a force on the A factor, at the A factor, the whole robot will be deformed. And this torque on each joint is used to resist this deformation. And also, so in the negative way, opposite way, this torque are resisting this external force, and it's move delta Q or delta theta for this displacement. So the work done, so this should be the same, and like it should be like opposites in opposite direction, but the magnitude will be same. So they added together will be 0. So if you can know this situation, we can come to next. We can write it together. So F times the X equal to torque times the Q. So we can write it together. And we take both transpose. And now we can recall what is the definition of a Jacobian. So the Jacobian maps the joint's velocity to, or we can say it's the joint velocity to the A factor velocity. Is it okay? And for a very, very tiny, small amount of time, so if delta t towards 0, a very, very small amount of time, so we can say that the J delta Q equal to delta X. Because the very, very small amount of time, so velocity, because we know velocity times time will be equal to the displacement. So if it's very, very small, we can say that the velocity is equal to the displacement. And then we substitute this. This will be delta. The delta means very, very small amount. So if we substitute substitute the Jacobian into our equation 1, then we can get F transpose times Jacobian delta Q equal to torque transpose times delta Q. So the delta Q can be cancelled out. then we can get I'll write it here. The F transpose times Jacobian equal to torque transpose. Then we can take transpose on both sides. Then we can get torque equal to Jacobian transpose times F. So is this okay? And this is all for the statics. Yeah, so we solve the statics. Yeah, so this Jacobian transpose maps the torque in the each joint to the external force. So if there's a problem is that if, like a robotic arms, if there's an external force applied on the main factor, then through the Jacobian transpose, we'll know what is the torque we need to apply in each joint, the motors. How many torques each motors need to apply to resist this external force. But the circumstances is this needs to be statics. So the robot cannot be moving. Because all the thing is we assume that the displacement is extremely small. It should be nearly no displacement. So it's in a static condition. So we already finished 50% of our lecture today. So we, yeah. So I know some of you need to do the statics of the robotics. So this is a very, very fast and simple method to map the joint torque to the external force. And now we come to stiffness. So I assume that the variation is negligible small. The torque needed to cause a change in the position of the joint. Point at local position is torque times the K2 delta Q. So what is the definition of the stiffness? So I don't know how many of you still remember what is the definition of the stiffness. So normally there will be two kinds of stiffness. The first one is, this is a beam. So if you apply a force over here, and will bend. So this is the deformation. And, or we can just call it, either use P, or you can use F, and you can call it W. So for the displacement, the stiffness is K equal to P over W. So it's a simpler, it can be understood as the ratio of applied force to the resulting deformation. So if your stiffness is very, very small, that means that if this stiffness is very, very small, that means same amount of force will cause a very large deformation. So if your stiffness is very, very high, so it's like maybe it's, so we can say the deformation equal deformation times the stiffness is equal to our force, external force. Or maybe we use F, it's easier to be understand. So imagine that we have very, very large number of value of stiffness. So if we apply a force if this K is very, very large, so our deformation will be very, very tiny deformation. That means that if you have a very large stiffness, then when we apply a force, the deformation will be very small. So this is the definition of stiffness. So why do we need to analyze stiffness in robotics? So like so sometimes like if we are using like industrial robots, so we need to like I don't know whether you know the impedance control. So usually in the industrial robots, the stiffness of the industrial robot is really high. So if the robot is like holding a very heavy object, then the deformation will be very, very small. Or else, if the stiffness of the robot is not enough, it's like when you grasping an object and it will be deforming. So the stiffness, if the stiffness of the robot is not enough, this robot will be deformed. So that's why we need to calculate the stiffness of the robot. And also, if we like doing impedance control or the force control, and also some like now we have cobots, the robot is working with the human. So in that circumstances or in that scenario, the stiffness of the robot should not be so really high. So if the stiffness of the robot is lower when it hits our human, then the robot will deform itself. So it will not like so hit it so hard. So controlling the stiffness of the robot is another major topic in robotics. And now we are calculating the stiffness. So this is the bending stiffness. And another one is the torsional stiffness. So torsional stiffness means the rotation. So we know that the rotation is a bit, this is the normal one. If we apply a torque, then maybe it will become like this. So the theta over here, so the torque divided by the theta will be equal to the rotational stiffness. We can say, like here we have is kq of k theta. So if we map, this is the torque, and this is the deformation in angular displacement, and between is the rotation stiffness. So there are two kinds of stiffness. And now the force relation between the actuator and the operation space can be expressed as the torque equal to the Jacobian transpose times F. This is what we already derived. So this is a static formula. And then, when the external force is exerting on the any factor, the deformation of the configuration of the any factor T. So this is the any factor. And it's equal to the Jacobian times the so T maybe is, you are not familiar with that. We can rewrite is the delta x equal to Jacobian times delta q. T is the delta x. And we can take the partial differentiation to the q, and we can get delta torque to delta Q. So this is, if you still remember, this one is the rotational stiffness. And here we have delta F and delta X. So this is the, if you remember this one, this is the bending stiffness. So we can substitute the two stiffness metrics into this equation. So for an ordered case, so if F equal to 0, then this is the rotational stiffness, and this is the bending stiffness, and this is how it's the equation comes. And for a loaded case, then we can have a Kc. And this is the F, the external force, and we can formulate this equation. So we can come back to this manipulator, this figure. So this is always about external force applied on the angle factor, and what is the relationship to each joint? What is the torque of the each joint? So when an external load, this is WE, is applied at the angle factor, the manipulation response by generating a constructive range denotes as WR to contract with the applied load. And the deformation T is composed from the actuation joints. This individual contribution aggregate to yield the overall resistance of bridge. So this is the relationship of this the deformation and the force. So together we can write our equation as, so the summation of the individual displacements. This is the deformation of the joint. So we know that for each joint, the displacement of each joint is delta Q, or we can say delta Qi. And if we times the Jacobian, then you can give us the deformation of the angle factor. Maybe we're not using the X, we're using the T as well. So like the I joint, deformation of the I joints times the Jacobian is the deformation of the angle factor. So we can sum all the I equal to 1 to, if we have n joints, if we add all the joints displacement together, this is our total deformation of the angle factor. So this is how the formula formulates. And the relationship between the external load and the resistive force of each joint based on the instant power relationship of the manipulation can be expressed as this. So we know that this is the range times the displacement. So force times displacement equal to the torque times the angular displacement. So this formula, this equation is the same as before. It's the same equation. So that the torque equal to, we can write it, the torque equal to the Jacobian transpose times the F. So this is the static equation. For the ith compliant joint, because we have some compliant joints inside, the relationship between the displacement and the resistive force, so it's equal to the delta Q equal to this K is the stiffness, invert times torque. And together, the relationship between the Q and torque can be represented in the metric form. So we can write it as this is the displacement of the external displacement of the n vector, and this is the range at the n vector. We can use the C-plane matrix to establish, and we can combine these two equations. So the initial relationship between the Ke and delta Qi can be established as this. So this all for the stiffness part. I know this maybe the calculation is more complicated. Is it? Is it okay for the calculation? Because all the thing we use is basically this formula. Torque equal to Jacobian transpose times force in our statics model. And the stiffness is one of the application of using the static formula. So any question for the stiffness part? But don't worry, because this is only for reference. If you are doing the statics in robotics, then you can refer to these slides. Or else our exam will not be covering here. Our exam will be only until the differential kinematics. Okay, so any questions? Any question for the stiffness part or the statics? How we establish the statics equation by using the Jacobian? So normally that we have already stated, if we want to come to the force domain, we need to calculate the acceleration. But through the Jacobian and the principle of virtual work done, then we don't need to differentiate with the time to get the acceleration. We can still get the relationship between the torque and the force. So we found a very, very interesting relationship. So if your Q dot, this is Jacobian, and here will be your X dot, then if we can see it, if the Q dot, if you differentiate with the time, then it will become torque, and it's equal to Jacobian transpose times the F. So F is equal to N times X dot dot. And torque is equal to M R times the Q dot dot. So it's quite interesting to get this relationship. Okay, so maybe we can have a break now, and for next, after a break, then maybe we can have some discussion for your final projects. Yeah, so you can have a break. And if you have any questions, you can come up and ask me. I know because today's we only covering it's all formulas, because the robotics modeling is just deriving the relationship and formulas with that. And if you have different models, then you can follow the steps, and you can derive your formula for your model.